Take it
Hi,
away.
my name is David Hoshijima, and this is our low-cost infusion pump. It's our capstone design, our senior design project. You got myself, Alex Helfenstein, Joseph Sidaway, Juan Sanchez, and Tanner Snow. And let's start with an introduction. Um, so, just for the general public, people may not be familiar with what a infusion pump is. Basically, it's just a medical device to uh, directly inject fluid into your body system in a steady and controlled manner, whether that's through intravenous, going through IV pumps, uh, pumps for insulin, for diabetics, and then the one that we're did our project on, the enteral pump, which we inject fluid directly, nutritional fluid directly to their stomach, their digestive system for the people who cannot consume food from their mouth. And this project is to be low cost, and when we were assigned this project, we were not given a ballpark of what kind of budget to stay at, or sorry, the cost of the product to be. So we started doing some cost analysis, looking into the average income in the United States, and looking at incomes in the developing nations, which included countries such as the lower part of China, Ukraine, Syria, and so forth. And we basically took that ratio and compared it to our benchmark infusion pump, which is the Moog's Infinity pump, which is retailed for around $500 to $700. And by taking the ratio of the income, we came to a conclusion that we want to have a product to sell for around $80 to $120, meaning that to give us a 200% profit margin, we want to fabricate and manufacture the pump for around $40 to $60. So from there, we then came up with our metrics for the project, which I'll pass the time off to Alex.
So to develop metrics for this, the first thing we did was we interviewed nurses, dietitians, patients, real end users to figure out what they actually want. And the second thing we did was we conducted a tremendous amount of research on products that were already on the market. And by doing this, like David said, we decided to benchmark against the Moog's Infinity pump. So basically, this thing retails for $400 to $700. Obviously, we wanted ours to be a lot cheaper. Under $40 was kind of the goal to get our final sale price. The Moog Infinity pump has a range of 0 to 600 milliliters per hour. But what we found when we spoke with dietitians and nurses is that 125 milliliters per hour seemed to be the ideal clinically relevant flow rate. So we wanted to try to hit that right on. Moog, they brag about their Infinity pump having a tolerance of plus or minus 10%. So we wanted to match that or better that. And then our final metric was Moog advertises a 24-hour battery life. We wanted ours to either match that or not use a battery at all, which is what we did in our design. So going on into that, the design we came up with to meet the metrics and what we wanted consists of three main parts. The first one is the pump housing. So basically, you take the bag of fluid, you put it in the pump housing, press down some springs, put a lid on. That applies pressure to the bag, and fluid can exit. The problem with using just this is it flows way, way, way too fast. So that brings us to our second part, the flow rate controller. So that goes on the cassette that's already on Moog's current bags. And basically, this does two things. It opens up an inline includer to actually allow flow to go. And then you can actually turn that knob and it squeezes the cross-sectional area of the tube so that the flow rate comes a lot closer to the 125 milliliters we're aiming for. Now you might have noticed, or some of you might have seen with this design, one major problem we kept running into is as the fluid empties and those springs expand, the pressure on the bag and the fluid drops. So your flow rate tends to start out really high and then end really low. So to compensate for this and take care of this, we developed a pressure regulator. And I will let, this is a major key component, and I will let Joe kind of get into explain the inner workings of that.
Okay, so if you can't see my mouse, but if you see the CFD model in the bottom left corner, that's sort of the model that we went off of. And what we're looking at here is called a downstream pressure sensing valve. So what this essentially does is where you see the red flow, that's our inlet at this section, and then the large cross section at the right side is our outflow. And this little chamber right here is a sort of pressure sensing chamber that is able to see what pressure is inside this section of the tubing and how it's affecting the overall flow. So the idea behind this is if the pressure gets too high, the force in this chamber, this bypass chamber, will push up on this piston, closing off this cross-sectional area a little more. When we first designed this, we had this entire section just to be the same cross-sectional area. But we saw that that wasn't nearly enough. The piston wasn't getting pushed at all. And it was basically just an extra set of tubing. So what we decided to do instead is we took the principle behind hydraulics, if you're familiar with it, where you can use a small cross-sectional area of fluid to regulate or to, let me rephrase that. You can use the different cross-sectional areas you see here on the left underneath the piston and the right where the pressure is being sensed. And that ratio is sort of similar to how hydraulics work. And you can sort of multiply the force that is coming on the wide area end. So we ended up figuring, after a bunch of prototypes, we figured out that a 2.5 to 1 ratio seemed to be moving the piston quite well and pretty sensitively. 2.5 ratio is, what I mean by that is this large end underneath the piston is 2.5 times wider in the radius than it is in the right section here. So we ran a bunch of tests on this, and Juan can explain our results and our test setup.
Okay, so yeah, I'm gonna share a video to see how our test setup looks like. I'm gonna stop sharing this for a minute. Okay, can you guys see this?
Yes.
Okay, let me know if it sounds okay.
Let's do a quick rundown to see how our prototype works. First off, we want to attach the range controller into the fittings bag cassette.
Can you guys hear
Basically, the cassette goes inside the range controller by going all around it. We want to make sure that we secure the flow before we close the door of it. So we'll turn this knob all the way clockwise. Once we know we're secure, we're good to close the door. Next step, we want to fill up the bag using 3 cans of nutritional fluid. 3 cans is approximately 1100 milliliters. Once our bag is completely full of fluid, we want to make sure that no fluid's going into the line. And we know we're good. First off, I want to show you guys how to pump using our pump design. We open our pump and we're then ready to load the bag into it. There's an outlet for the line from the bag in the right bottom, so that will help us out to keep the good orientation out of it. Once we're good and secure, we're good to close the pump. And then at the end, we attach our range controller in the side of it. We are now ready to attach the fluid line into our tolerance controller. One end will go from the bag into the tolerance controller's inlet, and the other end will go from the tolerance controller's outlet into our feeding port. In our case, we're pumping into a flask. I have cut this line for my convenience lengthwise, and so will the patients. Once we're ready to pump, we turn the range controller's knob counterclockwise in order to open it. We first prime the pump, and then once we get fluid going out, we adjust as needed. Since we're looking for a flow rate of approximately 125 milliliters per hour, which is a clinical relevant flow rate, we're looking for around a drop per second. You guys can see the line, fluids going in. We first prime it. Once we reach the glass, we adjust our range controller to obtain the desired flow rate. Okay, let's now look at a different approach. Instead of using the pump that we have already designed, we could actually use a pressure cuff or just simple gravity. I already went ahead and filled up a brand new bag with 3 cans of fluid. It's standing on this IV pole, which is about 3 feet from the tolerance controller. I already attached the range regulator into the cassette. And in the case that I would like to pump using simple gravity, I would just have to attach my inlets and outlets from the tolerance controller into the patient's gut and open the range controller, of course, and adjust as needed. But if we would like to use the pressure cuff, we'll first have to apply the pressure into the bag and then connect to the tolerance controller, respectively. The pressure cuff comes with a little pressure gauge. This pressure gauge goes up to 40 kPa, which is about 6 psi. So let's go ahead and apply pressure into it. Okay, so we have built the pressure. There's about 6 psi that's compressed in this feeding bag, and I already went and cut the line coming into the tolerance controller and out of the tolerance controller into the flask. We are ready to pump. We just have to open the range controller. You guys can see the line flowing. We first prime it. Once we prime it, we adjust as needed. Again, since we're looking for a flow rate of 125 milliliters per hour, we're looking at about a drop per second.
Okay, so let me get out of here. Okay, you guys can see okay?
Yep.
Okay. Okay, so let's go over the results real quick of what we have achieved. Let me zoom in. Okay. So as I said on the video, we have used 3 different pumping mechanism methods to test our range controller and our tolerance controller. So the pump housing that we have designed, we also already used the pressure cuff and we did use gravity. So when we're comparing results, we want to compare with the worst case scenario. So in our case, our worst case scenario is free flow, which is represented by epsilon, which is this magenta solid line on the top. And it's also represented by this dotted line, which is, it's theta. Okay, so epsilon, it's a free flow with no components attached to it, and theta, it's just using our range regulator. So we needed to throttle these down to 125, a steady flow rate of 125 milliliters per hour. So throughout the semester, you guys can see over here theta and eta. especially ADA. ADA represents the first version of the prototype that we ended up designing, the tolerance controller that we ended up designing for. And we quite liked the behavior of the curve, and that's why we have decided to go even further with this design. So as we kept on throttling down, we have achieved a steady flow rate. You guys can see over here gamma and beta, the magenta and the black solid lines. Those lines look quite steady, but they're not quite at the 125 mark just yet. We tried to throttle down even further, and we came up with delta. Delta is the red line right here. Delta, it represents a flow rate of an average of 123.5 milliliters per hour with a standard deviation of 10.5. And this particular case, this particular test was done using gravity, as I said on the video, 3 feet above the tolerance controller, with an overall tolerance of plus minus 17%. Let me zoom out. Okay. And now Tanner can go over the summary.
So yeah, so we started by trying to get the basic metrics from the Moog Infinity pump, and we, as Alex talked about, and so compared to our pump, we believe that we achieved fairly good success with our results, just based on the circumstances and what was given and available to us at the time. So the Moog Infinity pump, as Alex said, was about $400 to $700, and the overall cost of all of our key components together is less than $40. And the most expensive component is the pump housing, just because it uses so much material and off-the-shelf springs. But as Juan showed in the video, the patient can use a combination of any of these devices, of these components, to get the flow that they need. So the cost is really, it could be much less depending on a few factors of the patient. The range of our pump, compared to the Moog Infinity pump, we might not have as much range, but we are still able to hold a consistent flow rate, which is what we wanted. And we achieved that clinically relevant flow rate of about 125 milliliters per hour. We achieved 123.49 milliliters per hour, with an accuracy or tolerance of around 10 to 17%, depending on how you look at it. And so the accessibility of our pump was also a major factor, and as none of these components are electrical, so it is very accessible for developing nations and people who are may not have as much financial freedom to buy these expensive products, these potentially life-saving products, which is also a big deal. So there's a lot of future work that could be done, and a lot of our work was slowed down due to circumstances just in everywhere that everyone is aware of. But so some future work that we wanted to pursue was these would most likely have to be manufactured at a large scale. So we were hoping to pursue injection molding or some sort to create a more permanent version of these key components. A lot of our testing was done using 3D printed components, which worked just fine for the most part. But this injection molding would reduce the cost for consumers and provide us with these tolerances that would help the flow achieve what we wanted to. We had planned for more design iterations to further refine the ratio and the maybe ergonomics of the housing, but circumstances mainly limited us to focusing on the regulator and trying to get that down to the clinically relevant flow rate, which we did achieve. And then we were also looking into alternative methods of pressure regulation instead of our pressure regulator, which would include things like Tesla valves or other low flow rate mechanisms that maintain the flow and pressure. So overall, we would think that our project was an overall success just because we achieved pretty similar metrics to Moog for the most part, just based on the cost of our device though. So it really is, I think we've achieved pretty all right. So are there any questions about our project?